Okay, I think we can start. Thank you all for attending this tinyML talk. My name is Gianmarco Iodice. I'm the tech lead at for machine learning and also chair of the tinyML Global Meetups for the tinyML Foundation. And today I have the honor, honestly, to host this talk where Mohamed Shalan, the head of design and EDA of Efabless Corporation, is going to talk about the system on chip design for low power AI. In particular, we are going to talk about how to unlock tinyML with a cost-efficient approach to custom microcontroller design. So first of all, as I said, I'd like to thank on behalf of the tinyML Foundation and tinyML strategic partners for committing to take tinyML to the next level, and particularly to make this event as many others, virtual and in person, free for everyone, and to share the knowledge among the tinyML communities. In particular, here I want to thank ASIC, Arduino, ARM, BrainChip, AgImpulse, Efficient, Greenwaves Technologies, Gravity Inc., HiMax, ImageMob, Infineon, Inatera, NoteAI, NXP, PNG, PMIC, Pauling Technology, Qualcomm, Renesas, Schneider Electric, SensiML, Sony, Silicon Labs, ST Microtronics, Synaptics, Synchance, and TDK. So the most important thing, if you want to if you want to discover more about tinyML, in particular from the community around the world, is to join our meetup group, the tinyML meetup group, which today has more than 70,000 members around the world with 49 groups, which are very active to provide also in-person meetup groups and activities in the world of tinyML. It's also mentioned that we are also LinkedIn. So here, if you want to be updated on future events, opportunities, and technologies in this space, is definitely the other place you need to be. So the other important thing worth mentioning is about our YouTube channel, which now counts more than 10,000 subscribers. Because all the tinyML talks that we deliver are recorded, including this one, which will be available tomorrow. So in the YouTube channel, you can find all the previous sessions, and you can learn everything from the tinyML, from very starting presentation to discover more what is tinyML to very advanced talks in this field. So in terms of events, the tinyML Asia is certainly the one is approaching very fast, is because the 16th of November will be hosted in South Korea, in Seoul in particular. This will be an in-person event. So if you have the chance to be there, I really recommend to be there and to meet the inventors and the leaders in the Asia area. So as also mentioned in other tinyML talk, this is an important report that have been crafted recently to describe what the state of the art for edge AI, including tinyML. This is a report that you can download for free, and it gives you everything you need to know in terms of technology, which are promising to bring machine learning at the very edge, keeping in mind the low power consumption and cost and privacy at the same time. And now I'm going to introduce Mohamed Shalan, who is the head of design and EDA at Efabless Corporation. For his role with Efabless, Mohamed held various engineering positions at several organizations, including Mentor Graphics, Motorola SPS, and Mindspeed. Mohamed holds a PhD degree in computer engineering from the Georgia Institute of Technology. His research interests are multi-phased, encompassing open source EDA, hardware, and software co-design for embedded systems, with a strong emphasis on low-power computing. His contribution to these areas have resulted in over 40 peer-reviewed publications and 3 US patents. It's my pleasure to introduce you, and I'm very looking forward to learning from you.
Yeah, thank you very much. Okay, so hello everyone. Good morning, good afternoon, and good evening, wherever you are. Today I'm gonna show basically how you can design custom microcontrollers that basically are suitable for tinyML applications, and you do this basically without all the barriers and the problem basically typically associated with custom microcontrollers or custom SoC designs. So as you all know, microcontrollers are everywhere, and they are these tiny brains that power things like cars, like appliances, and doing like plenty of different functions. And it's estimated that the number of microcontrollers out there around like 300 billions. And eventually tinyML is considered as basically the current wave that drives the growth of the microcontroller sector. But the question, are microcontrollers actually are good for this and ready for tinyML wave? Eventually, microcontroller vendors, they address this through different things. By basically trying to make the microcontrollers more customized to fit this class of applications. Typically, basically, when you have machine learning model in the inference phase, and this basically done through instruction set extensions, having accelerators that can be implemented into embedded FPGA fabric, as well as basically providing fixed or programmable machine learning accelerators. And the idea is eventually is trying basically like to basically make the microcontroller basically very efficient in terms of performance and power consumption when it comes basically to running machine learning models in the inference phase. But the thing is, however, all of these solution microcontrollers are still suboptimal. And actually, basically, I'm borrowing here like a slide from Professor Frank Vahid, where basically we're like discussing the difference between basically having different processing elements to implement certain functionality. And this basically we have like wide spectrum, starting from general purpose processors to custom processor that basically does nothing but the specific function. And in between, we have the application-specific processor, and actual microcontrollers falls under this, with all basically the accelerators, all extensions, all the things that we put into microcontrollers to make them basically perfect fit for the application. But the problem is, from the economical point of view, it's very hard basically for microcontroller vendors eventually like to provide a microcontroller for every application out there. So what they are doing, eventually they create families where every family eventually targets a class of applications, and then in each family we have members, and eventually as an embedded application designer designing an application for using microcontrollers, you basically you select the vendor, and then you select the family based on the application that you are targeting, and then you start basically to pick one of the family members that basically fits the application perfectly. However, if you go and you do your custom microcontroller from scratch, eventually you're gonna gain the benefit of having basically the most efficient implementation for your function, because eventually custom SoC, they come with lots of goodies. So we eventually get the best performance, the most efficient energy usage. Eventually have the opportunity to move functionality from the board into a chip. So eventually that will reduce the total overall cost of your system. You can add basically security measures into your implementation, so to make it basically very hard for basically hackers to get into your chip, basically copying your design or eventually like exploiting things. So eventually this is something like very important. Also, as you are doing everything from scratch, you can have the differentiator, which basically makes your application unique and basically compared to your competitors. If you go for mass production, eventually, like having your custom stock is basically is the way to go, like compared to buying like off-the-shelf microcontrollers. So in terms of like the overall cost for the parts, eventually, your custom microcontroller basically will cost less. And in addition to this, eventually control your supply chain, because eventually you own the chip, you own the design, and it's all about basically having access to the foundry, eventually to basically to fabricate your parts, and then basically whenever basically you need, if you run out of stock. And you don't basically depend on suppliers or even like vendors eventually like to provide you with this. And eventually we most of us experience basically problems like during the last pandemic, eventually related basically to supply chain interruptions and the delays basically in product introductions basically because of that. So eventually if you have your own custom chips, and basically eventually you are basically, well, you can be hit by this, but not basically that severely compared to that basically buying off-the-shelf components. However, like taking the ride of custom SoCs is not that easy, or not that like smooth. Eventually it comes with its own problems as well. So I can list some of them here. Eventually, you have very high cost, especially basically the non-recurring engineering costs. This is the cost that you need to pay upfront. Eventually, for tools, for basically for IPs, for things basically to get you ready, basically like to do the design, and then when you do manufacturing, eventually also you need to pay upfront basically the cost of the masks. So all of this eventually contributes to the total cost before even you produce the first parts. You need to have access to the foundry, basically for your fabrication, and to have access to the PDK for the process that you are targeting. And eventually you need to basically to sign NDAs and negotiate basically terms and deals with the foundry, which basically is not basically an easy thing, especially if you are basically like a small entity. IP access, eventually to have design and want to accelerate the time to market, you need to rely on IPs, and eventually you need basically to get these IPs. And IPs, yes, we have some open source IPs, but eventually you are by your own, because you need to validate them, and in order to use them, so they need to be qualified. And basically, if you want to basically get over this, eventually you need to go for like commercial IPs with support, and this also will cost basically lots of money. The design itself is very complex and requires expertise, which eventually will add to the total cost basically of doing this. And then you have the risk is very high. Eventually, that's you do a custom chip, and eventually. And especially if you're doing it for the first time, and eventually like you didn't get functional, because basically you have to like problem design that you basically didn't uncover them basically like early on. So you basically know about them when basically you have the silicon back, and you figure out that basically something that basically was done wrong during the design. Plus other cons for basically going for custom SoCs. So just to summarize, there are 6 enablers for any custom chip, and these eventually listed here. So you have the market access, expertise, IBs, EDA, PDK, and eventual access to manufacturing and packaging. And eventually solving or having basically enabled some of these 6 items, eventually not enough basically to have in order to enable you to have your custom chip. And typically, who was basically the entities that already do basically design chips and basically manufacture them. They eventually they establish already a relationship basically with different EDA vendors, with different IP providers and different foundries, and eventually and this basically done through basically contracts and through NDA agreements basically signed between them, and eventually and this basically takes time and money and effort. So at Efabless, eventually we realize all of these issues basically that prevents anyone basically to go for custom silicon. And basically, we have this goal basically for simplifying chip creation and opening it to everyone. And when we say opening it to anyone, eventually we want even people with no background basically in chip design to be able basically like to do basically design, and basically will help them to do this. So so basically you don't need to be chip designers eventually to chip and manufacture, fabricate chip and eventually validate it and test it afterwards. And eventually, as I'm going to mention, eventually already demonstrated that we have basically people who basically didn't have any experience, and eventually they did that basically with us. Okay, and definitely if you are basically know what you're doing, this even will be even more simpler for you, because eventually we're going to basically handle all the 6 enablers that I mentioned earlier. And in order to achieve this goal, eventually we started with constructing basically a large community of designers or people interested basically in custom silicon. And eventually, as we grow this community, eventually we increase basically with this basically the creativity and the productivity, and eventually this basically big community of people who basically are experts in designing chips or interested basically in custom silicon. Eventually, they can help each other so that they can co-design custom chips together eventually basically to target basically smart products, including basically products basically that fall under tinyML. And eventually at Efabless, eventually we help them basically take these designs and convert these designs eventually into chips through basically offering them a path to basically to the foundry and give them access to PDKs, and eventually not only that, also we provide them basically program to fabricate chips for prototyping or for low production runs basically at very low cost. To summarize, eventually we give the community or anyone who is interested basically with custom silicon basically complete path from design to validation. So you can start basically, we have a design idea. You can basically use either your basically open source design tools that we already provide, or if you want, also you can use proprietary EDA tools, or you bring your own tools to do your design. Eventually, you need only to focus on the design. You need to focus about how this design basically will be mapped into silicon, how the input and output basically will be done, how to bring up the chip okay, when you have it on hands. Because eventually we provide you with something called Caravelle, which eventually is like a template chip that eventually contains everything that basically enables you to have like basically successful custom silicon. And all you need to do is just basically focus on how you design your basically your idea, and to fit basically this empty space, which here, for example, like 10 square millimeters. And eventually, once it's integrated, eventually you can just submit it to Efabless platform, and then eventually this will be fabricated and then packaged, and then what you get packaged parts as well as basic evaluation boards like this one. Okay, so everything basically like during this basically is we provide the help, the community provide the help, and also basically. Once you submit your design, eventually everything basically is managed behind the scene for you. And so once you submit the design, and the design basically is verified to be good, eventually in terms of basically in terms of being ready to be manufactured, eventually it will be basically fabricated, and then you get back, as I mentioned, the parts and the evaluation boards as well. Okay. So this way, eventually, like we don't let you start from the first floor, go to the 20th floor. Eventually, you start basically from the 18th floor, because what you do really, you just focus on what you will be doing, the functionality that you want to implement, and then basically don't worry about anything else, because this eventually we're gonna take care of the rest. So the Caravelle SoC that I mentioned eventually has at the bottom, as you can see, we have this hole where basically you have the like 10 square millimeters silicon that you can use it the way you want. But at the bottom we have It's like small system on chip that contains small CPU memories, basically few peripherals, and these basically are necessary eventually to power up the chip and basically to provide like configurations for the input and output pads. You can use you can use it basically also based on some firmware which eventually can interact with your design, maybe for controllability, observability when you do testing, or you can basically, your design could be basically nothing but like an accelerator or an IP which eventually sits on the bus, and then eventually the whole chip for you eventually is the SoC that already comes with the Caravelle, as well as basically what you add on top of that eventually, like to basically like to customize it for your application. However, basically, not everyone basically wants to do this because eventually there's some advanced users who are basically, they want to have basically the whole silicon area, which basically 15 square millimeter, for them basically do whatever they want. So what we will provide them, basically with an empty Caravelle, what we refer to as open frame, where basically we provide the pad frame, and this basically, the pad frame contains the input-output pads. So we have basically fixed configuration for the input-out pads, and eventually you can use this silicon the way you want. Or if you are even more advanced than this, eventually you can we can basically configure the pad frame for you, where basically you have basically the 15 square millimeter as a whole for you. You do basically whatever you want to do with it, even when it comes to IOs. Also, we provide, as a part of what we offer basically to help the community, we provide OpenLane, which is an open source flow, which basically tries to make the chip design basically a push button like process. So when you basically do your model or describe the hardware that you want to like to build or implement into silicon, and eventually you can just give it to OpenLane, and this is basically what the RTL files that describes your design, and eventually OpenLane eventually will take it through different steps. These different steps implemented either using open source EDA tools, and in this case where you basically, it uses OpenRoad EDA toolchain, or if you elect basically for basically commercial EDA, you can we have like a newer version of OpenLane, which is OpenLane 2, which eventually like has support for commercial EDA. And eventually through our platform, you can use like Synopsys EDA tools basically for your design if you want to do that. Again, to make things and basically to provide more enablers for you, eventually we'll provide basically a library of IPs. These basically like open source IPs or obfuscated like commercial IPs and these IPs eventually they are qualified and validated. So when you use them in design, basically you know that basically they will function as basically as described, and basically you won't have problems basically like using them. And eventually these IPs eventually they basically they package in like in a standard way, so they basically make them like very easy to like to use. And eventually building your design basically utilizing these IPs eventually will make basically will make the time to market basically very short, and accelerates your design cycle. And all of these things eventually they are packaged together basically in a program that we refer to as Chip Ignite, which basically is Rapid IC creation program, which eventually enables you basically like to do designs for custom silicon utilizing everything I have just mentioned, and basically this is for a Skywater Sky 130 process. And so basically everything you have access to, you have the IPs, you have the tools, you have access to the foundry through Efabless. You have eventually the starting point, which is Caravelle, whether basically it's Caravelle with the built-in small SoC or the Caravelle open frame. So you have the 10 or the 15 square millimeter. And eventually you can eventually go for rapid prototyping, and this basically costs less than $10,000. And for this, you get basically 100 parts, basically with QFN package, as well as the 5 boards. And we basically have another option where basically if you go for low volume to get basically like 1,000 parts. And this basically also plus boards, and eventually you're gonna basically this will cost like $20,000. So over the past 2 years, eventually with this community, eventually we have like around like 10,000 community members. We have basically they did like 1,000 designs, which resulted in 500 chips. And these basically designs, they are available to anyone eventually like to use them as a starting point and build basically just customize them. Or to learn from them, and eventually you come with your own to basically to solve your basically problems, or to create like customization for the application that you're targeting. And these are basically examples of designs done by the community. And here, eventually, this is something that we did with the IEEE Solid State Circuit Society, when basically we ran together basically the Chipathon, where basically invited basically IEEE student members from over the world eventually like to compete, basically creating designs. And we did this, and lots of designs basically were resulted on this, as you can see here. And that was basically in 2021, and then that was repeated again in 2022. And all of these designs eventually they are open source and eventually available to anyone to reuse, or eventually use it basically as a starting point, basically to do and customize them, basically do something else. In addition to that, we have basically like all the designs that basically done by the community, and they are basically fabricated. Eventually, they are already listed basically in an online catalog, which is accessible on Efabless website, just by following this this URL. And there, basically, you can search, you can filter. Eventually, you can find basically like the 1,000 designs basically I was referring to. We help you basically like do custom chip, but where is tinyML in here? So we are really eventually like to basically like to listen about tinyML, like where tinyML here, other than basically we're gonna do custom microcontrollers, which will be efficient to do this. Eventually, like we realize basically tinyML is the basically next way for microcontrollers and for eventually for custom SoCs. That's why basically we start creating a tinyML reference flow for Chip Ignite program, where basically you start with the data eventually like for your model and the requirements, and eventually you go through the step of software development, which involves model development, evaluation, optimization, and then the model basically will be converted into C++ to run basically on your custom microcontroller, and you write the application based on the requirements. So we start with the basically software development part. Eventually, and then you move basically to the hardware, where basically the model that you already basically designed and optimized eventually imposes more requirements that eventually can be captured in easy to use format, which can be passed to something called the SOC builder, that eventually can take this high level description and basically constructs this custom microcontroller, custom SoC for you, and generates the RTL, as you can see here, and eventually this is basically using the IP library, which eventually contains IPs for different peripherals that your application might need, as well as basically accelerators that your eventually the target application might need as well. Once you have the RTL, eventually you can perform FPGA validation, where basically you can have your RTL eventually implemented into the FPGA. Your software that includes the machine learning model will run on basically on top of your SoC design, which is mapped into the FPGA, and eventually you can basically do validation of your basically of the SoC, which was basically generated for you even before basically going for fabrication. When basically everything is okay in terms of like FPGA validation and verifications, eventually you can take this into the physical implementation phase using OpenLane, where basically this flow that eventually can use open source or commercial EDA, eventually is capable of basically of taking this RTL and generate GDS, which eventually can be sent for fabrication after, as I mentioned in the previous slide, 95 days, eventually you can get back your silicon. But as you're waiting for the silicon to come back, eventually what you can do, you can use the FPGA implementation eventually to perform, basically to do pre-silicon development, so that basically you can eventually enhance your application, you can add features, you can do lots of software development, basically like waiting for the silicon to come back. So to validate this reference flow, eventually we decided basically like to create like a reference SOC, reference design for SOC for tinyML. And eventually wanted to target application that involves basically machine learning models to process low speed sensor data, including audio signals. And also we want to basically to have basically some security accelerators on board as well as basically we have accelerators for machine learning. And eventually, like in the reference flow that we started, and I showed in the previous slides here. Sorry. Like here, eventually, like we're using something called basically NNOM with the Keras, eventually like for this flow for the model development. So eventually we created accelerators eventually to accelerate the operators and the layers basically in the NNOM. And eventually the SOC builder eventually will take only basically the needed accelerators eventually that match basically the model that was created as a part basically in this flow. Also, the SOC basically architecture was optimized basically for that data movement and for low power operation as well. And eventually this basically will be used then basically as a reference design, which eventually can be used by anyone basically to basically like as a starting point. Okay, basically like to create like their own custom microcontroller. This SOC eventually we like so far we went through 2 iterations. The first iteration eventually resulted in a tape out in basically last September, and eventually we are waiting for the silicon to come back. And eventually here in this iteration, we basically the Cheetah SOC eventually was implemented as a user's project in the normal Caravelle chip, which basically occupied this top area, which is the 10 square millimeter. And then we have basically the next iteration or next generation, where basically we did lots of optimization when it comes to like to energy usage. And basically increase the performance in different aspects, basically, and then we moved from being a user project in Caravelle chip into a design that occupies the whole basically chip, and for that basically we use the open frame. So this basically a design is work in progress, and eventually basically the target tape out is the early November. So eventually we are basically like around like a week basically away basically from the tape out. And eventually this demonstrated that eventually like using this reference flow, using all the enablers that I mentioned, eventually you can basically like do iterations so quickly. So eventually like the first iteration was in September, now it's November. So basically it's like 2 months basically like to do basically like iteration, which eventually like very powerful basically. And it's not basically done like this way basically like in basically in other environments. So I think that's it for what I wanted to cover. So if you have basically more questions, or you need to learn more about Efabless offering or Chip Ignite program, and you learn about all the technologies basically that I have just mentioned, eventually you can just scan this QR code. Also, you can join the open source silicon community. which basically Slack community that basically, and then start interacting with the community and basically learn from them, and basically like collaborate with them eventually, like to do your custom silicon. So yeah, I think that's it. Thank you very much.
Well, thanks a lot, Mohamed, for the brilliant presentation. It was absolutely very good. And we also have some questions. I would say let's start straight away with the questions we have in the Q&A box. One of these is about which FPGA boards are supported.
Okay, so currently we, for the reference flow, I have just mentioned, we are using the CMOD 7, which has the Xilinx RTX 7. So this is supported. Also, basically working on supporting open source FPGA boards based on the lattice ICE family. So this basically will be coming soon as well.
Okay, thanks. Okay, let me flag it. Okay, so what are the design norms like ISO and standards IEEE to adapt in modeling the minimum viable product technical draw plan while the life cycle development process steps for an Efabless chip project? Of course, you can read the question in the Q&A box if you want to, because it's quite a long question.
I'll take that one. So I think the question is referring to the process for developing a commercial product from, because it's referring to lifecycle development process, commercial development product from the test chip environment. And so the process is the user goes through MVP to prototype silicon through the flow. And then if they've adopted the Caravelle infrastructure or the infrastructure of the open frame, they're in an environment where we've previously qualified a flow and qualified a chip development platform. And so the process to go through the normal backend qualification of silicon is faster because they're provided an environment in which to do it. They've got boards, infrastructure, test processes, packages, sockets, all the normal elements of a qual process available pre-canned on a board environment to be able to go through the qual. And the normal product development process and cycles, but expedited by the fact that somebody else has built all the infrastructure for you and you're reusing it.
Thanks for answering this question. Let me go to the next one. What low power functions does Cheetah system on chip have?
Okay, so at the moment, eventually we have basically we employed like clock gating. We have eventually we plan, but this is not for this iteration. Basically, for the upcoming iteration, basically power gating will be implemented, which basically will support which like these together basically will add more low power modes. We have basically like peripherals, which basically will and accelerators, which eventually will that operate without the need for for the CPU and the most of the system. So eventually they can be put in low power mode and leaving basically the other functions basically to transfer data and to do data processing without the need for the rest of the system. When it comes to implementation, eventually we have some basically we are using some open source tools that we developed basically internally that eventually capable of doing something like automatic clock gating for registers with enables, basically like to reduce the automatically basically to change the gate level after RTL synthesis, basically like also to reduce power consumption. So basically these are like in short basically what are the features that we have basically in Cheetah at the moment.
So what type of OS license is it? Can this be used for commercial developments?
So this is for you, Andy.
So right now, the Cheetah ML SOC is not 100% open sourced. And so we have an open source version that we're working on. The ML SOC we currently have is proprietary. and we're working to figure out how to parse the market so that there's some portion that's available in open source and some portion that's proprietary, depending on the feature depth that's needed by the users. So intent is to have two vectors, one proprietary and one open source. I hope that answers the question. And the open source is Apache 2.0. Yes, it's usable for commercial developments with attribution.
Thanks. The next question, actually, it was also a curiosity on my side. Let me just, okay. Do you also provide support for mixed signal design? If yes, then which tech nodes are supported? GAN-based or RF-based designs?
I'll take that one as well. So yes, we support mixed signal design, although in a very limited basis for this kind of chip. And so we've got to be very, very careful about how difficult the qual gets based on what you change on the chip. So if you go all the way to the configurable pad frame and you change power supplies, it's very hard to reuse the hardware. If you use the existing pad frame power supplies and design in a mixed signal manner inside of that, it's fairly easy to reuse the qual hardware in most scenarios. We support RF-based designs, not GAN, and there's one technology currently supported. It's Sky 130, which is an open source technology from Skywater.
Slightly related. What would be a suggested option for mixed signal developments? I think you have probably already covered this in your...
Yeah, I think reasonably covered.
The next question is about what if the solution doesn't fit in one chip? Is there a way to scale? It's a good, interesting one.
So we have had a very small number of customers ask us about something bigger than 15 square millimeters. And it's absolutely possible, obviously, to hook 15 square millimeter chips together in a SIP and have multiple modules that hook together on a platform. But currently we have very, very limited demand for a larger than 15 square millimeter implementation on 130. And if there's demand, we will make it. So if there are multiple people who want to come down the pipe and say we want to build a 30 or a 60 square millimeter die, and there are enough of them to justify doing it, we will absolutely build that platform.
So the other question I have here is, well, actually I have two questions. What is the process in order to apply for the init chip program from the Efabless platform?
Go to the Efabless website and click on the Getting Started link and log into the platform and create an order with a deposit for $200. And you will be immediately involved in and on the process to doing your chip ignite.
And is there any selection criteria in order to be an eligible candidate for the program?
Well, you've got to be able to do your design in a manner that will fit into the current platform. So it's got to fit into either the Caravelle or the open frame scenario on the Sky 130 implementation. And it's got to be compatible, obviously, with manufacturing that technology, right? So you can't do something that we can't get through the DRC rules or through the foundry acceptance criteria. And it can't require manufacturing layers that aren't in the current technology. But other than that, it's a commercial process, and you buy it, we make it, assuming that it fits into the plan. There's no restriction on the number of slots that you order or on the availability of tape-outs.
Thanks. So here again, we have two questions. I'm going to read the first. So what is the software tools that you recommend to use while the MVP for the chip project?
I would strongly recommend, if you've never followed the flow before, to go through the open lane flow development for an open source project. And there's a suite of tools that are provided to you as part of the getting started process through the Efabless platform. And it's a very well recognized suite of open source development tools. The OpenLine Flow bundles with it the entire tool set. And so you'll get a very good starting point just by clicking on the getting started and going from there.
And the question that follows is, what is the extension format project file to submit for the Efabless chip project?
So there are multiple accepted or required file formats. You've got to give us enough data for us to be able to get the layout submission and the netlist to be able to do LVS. And so plus, the documentation that's required to be able to get through the tape-out process, which is a very limited set of paperwork. But that's it. We don't need a lot of data on your design. So I think the correct answer, Mohamed, GDS and LVS netlist?
Yes.
Okay, many questions. We have addressed all of them in the Q&A box. Well, probably on my side is for people that are they like to design their own solution for tinyML. Do you have any recommendations for them if it is the first project of this type for tinyML in particular?
I'll give one, and I'll let each of the other guys give one for sure. Mine would be get started. The barrier to going through the process is literally as low as clicking on the button. We've had everybody from high school students to literally some of the lead researchers with PhDs on AI and ML development in the world go through this process over the course of the last 3 months. And they find it roughly equally complex. It's easy for everybody. So, click on the get started, get moving, and understand what's possible. It's like opening ChatGPT-4 for the first time, typing something in and realizing, wow, this exists. And it will change your perception of what's possible from a silicon development perspective.
Thanks a lot.
Mohamed, do you guys have an equivalent to that?
Well, I think it's well said, you say it all. Yeah, just get started, and eventually, everything is there. And yes, actually, I like basically that, the analogy with using ChatGPT for the first time. Yeah, basically you're gonna be able to do things that's even though that we have basically very little experience about ASIC design, or even with no basically experience at all, because we already did that with basically some community members who did it for the first time. So yeah, you just hit on the get started, and we'll take you from there.
So there are other two questions. One I can answer is the question about the slides and recording. Yes, this session has been recorded, will be available tomorrow in the tinyML YouTube channel. And also the slides will be available in a PDF format. About the question for you guys is, what are the qualities tests to apply in the technical draw plan MVP in order to grant performance for the Efabless chip project?
So the chip design goes through what I'll describe as a normal development process. So you design an RTL base. We expect that you verify your own RTL. We synthesize that RTL. We check that the synthesis netlist is equivalent to the RTL. We implement the RTL. We verify it physically. We produce a design, we verify the timing for that design, we implement the design to a GDS, we verify that the final GDS is, with extraction meeting timing, and we verify that the final GDS is meeting, DRC, ERC, etc. rules. So it goes through, from a silicon perspective, a normal suite of verification. I think the one thing that was kind of historically present in 130 nanometer that's not currently present in our flow is an IR drop flow. So if you have a very high power consuming block right now, that's not present as part of our default chip development flow today.
Thanks. And is 95 days the hard max to get the design?
No. So there's two package scenarios today. One is a WLCSP and one is a QFN. There's a range of packaging times depending on whether the lot has gone through an expedite process or a normal fabrication process. I think the median time to get silicon out right now from all of the tape outs we've done is about 130 to 140 days. That'll give you an idea of median. I think the best we've achieved is somewhere between 95 and 100. And I think the worst we've achieved is somewhere north of 1 year. So there's a range, but that median is about 130 days.
Any other questions from the audience? We have a few minutes before closing this very interesting session. Interesting also in light of the questions you have received today. Let's wait just a few more minutes and before ramping up.
Well, if I may just make a comment, this is Mohamed Qasim.
Absolutely.
It is indeed very straightforward to start. It is actually, I encourage you to try and get in. It takes minutes to be set up. It takes under an hour to try and run your first example and actually get an outcome that will go into a chip. And then you can start from there and modify and apply, get your own RTL or algorithm baked in. So it is I recommend that to consider that the emotional barrier of starting is higher than actually starting and getting something done within an hour or two at the most. And it is a different experience. Please join the Slack channel, and give it a try, and ask questions or give us comments.
Thanks, Mohamed. Okay, we don't have any more questions. I think
somebody was just asking to put up the QR code back again.
Yes, absolutely. Mohamed, do you want to change the slide?
Yeah, sure. Let me try.
Perfect. Okay. So I'd like to thank you again for the presentation, brilliant presentation you have delivered today. It was my pleasure to host and moderate this talk. I think we can proceed with the final slides to close this tinyML talk. As I mentioned at the beginning of this session, we want to thank the tinyML strategic partners for making this event, but also many others around the world possible and free in many cases to the tinyML communities to learn more from the experts in this area. In particular, I want to thank the executive strategic partners, which are Qualcomm, Synchant, the Platinum strategic partners, Sony, the Gold strategic partners, ARM, Edge Impulse, Infineon, Innaterra, Renesas, ST Microtronics, Synaptics, and the Silver strategic partners, which are ASIC, Arduino, BrainChip, Efficient, Greenwaves Technologies, Gravity, HiMax, ImageMob, Not.ai, NXP, PNG, PIMIC, Pauling Technology, Schneider Electric, SensiML, Silicon Labs, and TDK. And with this copyright notice, I'm going to close today's session. Thanks again, Mohamed, for delivering this session. It was absolutely a pleasure. I learned from you, and I'm pretty sure also the audience learn as well. With this, I'm gonna say hello to everyone. Looking forward to see you at the next tinyML talk.
Thank you.